Muchas gracias, Alberto, por la presentación. Bueno, aparte de darles la bienvenida, quería comenzar comentando un poco de dónde sale la iniciativa de estas charlas. Yo soy coordinador de posgrados de la Escuela de Ingeniería Mecánica de la Universidad Industrial de Santander y formo parte de la Red Colombiana de Investigación en Fatiga y Fractura, que pues ha nacido recientemente como una iniciativa para encontrar espacios comunes de investigación entre la universidad y las empresas. Allí en la diapositiva pues ustedes ven una imagen de los participantes en esta red con un fuerte balance entre el desarrollo de teoría y estudio académico y la contraparte industrial, que pues finalmente son los que están llamados a aprovechar estos avances y este proceso de apropiación tecnológica. En particular, en la Escuela de Ingeniería Mecánica de la UIS hemos tratado de incentivar este tipo de actividades, las redes de colaboración, todo dirigido a, por un lado, pues mejorar los indicadores de investigación de nuestra región, pero también a realizar ese proceso de transferencia que tanto hace falta en el tejido productivo. El día de hoy pues vamos a iniciar este ciclo de conferencias, como comentaba Alberto, con un investigador muy cercano a nosotros, Sundararajan Natarajan, que es profesor asistente del Instituto Indio de Tecnología-Madras. Él trabaja junto con otro grupo de investigadores en el Legato Team, y en particular pues a través de la escuela hemos realizado la gestión para dar comienzo a esta red de conferencias de la Red Colombiana de Fatiga y Fractura. Entonces, pues es para nosotros un placer tener aquí el día de hoy a Sundar. Él nos va a comentar aspectos referentes a la mecánica de la fractura y cómo se está tratando este tema desde el ámbito computacional o mediante el uso de métodos numéricos. Antes de comenzar, pues hacer una presentación formal del conferencista. Él es profesor asistente desde el 2014 en la sección de diseño de máquinas del Departamento de Ingeniería Mecánica del Indian Institute of Tecnología-Madras. Esta universidad está clasificada entre las primeras 300 universidades del mundo y es la primera universidad en ingeniería en la India. Pertenece a una red de universidades de alto desempeño académico y, bueno, tiene un amplio reconocimiento en Asia. En particular, el profesor Sundararajan Natarajan es un investigador que tiene más de 135 publicaciones indexadas en Scopus, con un factor de impacto H-index de 34, y él ha estado dirigiendo su investigación en temas relacionados con mecánica de la fractura, métodos numéricos avanzados para la resolución de este tipo de problemas, que es el propósito de la charla. Aquí hablarán de XFEN, Facefield y otros similares. También tiene publicaciones muy reconocidas en el ámbito de materiales compuestos y materiales funcionalmente graduados. En su experiencia, pues él estuvo trabajando varios años en General Electric, en la división de aviación, como ingeniero. Posteriormente estuvo trabajando en Cardiff University, en la Universidad de New South Wales y en el Instituto Indio de Ciencia en Bangalore. Con esto, pues, darle nuevamente la bienvenida a Sundar. It is very nice to have you here with us. I hope we can continue our collaboration, and I can now give you your time for the speech. La presentación para los asistentes se realizará en inglés. Pueden activar el closed captioning de Google Meet, por eso escogimos esta herramienta. Y adicionalmente, si tienen dificultades en seguirla, también pueden activar la traducción de esos subtítulos en el video, ¿de acuerdo? Entonces, bueno, con esto yo creo que ya podemos comenzar. Sundar, are you there?
Yes, I'm very much here. Can you see
Okay,
me?
so now I'm going to start sharing my presentation, and I'll give you space to share yours and start with the talk. On behalf of the Colombian Network of Practical Factor, we would like to thank you again, also Universidad Industrial de Santander, and we hope we can continue collaborating with your university in the near future. Thank you for accepting our invitation, and you can present now.
Good morning, everyone. Thank you for this great opportunity, and I hope everybody is safe and sound with your family amid this pandemic situation. Am I audible?
Yes, you are.
Okay, all right. So thanks for giving me an opportunity to present my work at Columbia Network for Fracture and Fatigue. And it's my great pleasure to talk about some of the research activities that I have been doing here at IIT Madras. Some of them have been started during my PhD work, and during my postdoc, something else I picked up. So I'll be giving a short overview of different techniques that or methodologies that we are working on for modeling fracture in this talk. So let me start presenting my screen. Let me know if you're able to see my screen.
Yes, we can see your screen now.
Okay, thank you. So the title of today's talk is going to be on recent advances in computational fracture mechanics. I'm Sundararajan Natarajan. I'm a faculty in the Department of Mechanical Engineering at Indian Institute of Technology, Madras. And that's my recent picture. The picture that you saw and the invitation is quite old. And this is how I look now. Once again, thank you for the great opportunity. So this is where I am currently located. Actually, I'm in the south of India. And hopefully, pandemic situation becomes better, and hope to visit Colombia sometime. It's been a really long time. I think last time when I met Andres, that was in 2018 at WCCM in the US. So hope to visit you in the near future. So I'm going to start my talk by giving a quick overview of Indian Institute of Technology. So this is one of the premier institutions in India. This was established in 1959, and it's currently ranked #1 in India. We have around 550 faculty members, hosting around more than 8,000 students. The beauty of this is that it's amidst a forest. So there is a 250 hectares of forest campus. So both campus, the students and the faculty reside on campus. There's a nice picture of the deer on campus. We have 9 engineering departments, traditional departments like civil, mechanical, and electrical. We also have aerospace, chemical, computer science, engineering design, metallurgy, and ocean engineering. We also have 9 other allied departments: applied mechanics, physics, mathematics, chemistry, humanities, and management studies. And I belong to the mechanical engineering department, where we have 6 research focus groups. We are around 65 faculty members with around 350 undergraduate students and little more over 500 master students, which are basically MTech students. And we also have little over 500 research scholars. So we have 2 types of research programs here at IIT Madras. One is the traditional doctoral program. We also have Masters of Science by Research, where the student is expected to do original research as a part of their master's program. And there are 6 research groups: advanced computational engineering, materials and design, manufacturing science and engineering, dynamics, acoustics and controls, energy science and engineering, and micro nano bioscience and engineering. Although I sort of fall into all the research focus group, my primary focus our affiliation is towards the first focus group, which is computational engineering. We also have specialized centers for rehabilitation devices, non-destructive testing, and also on combustion research, which is like unique in India. So all said about my institute. This is my research group. We have a small 9-member group with 1 postdoc, couple of Master of Science by Research, and the rest are PhD scholars. Most of them have graduated, so this is really a bit old picture now. But nonetheless, they are still active part of the research group. We are still working on some problems that we started during their work here at IIT Madras. And before I start my presentation, I'd like to thank my collaborators. The first one is my PhD supervisor, Stephen Bodes, postdoc mentor, Chongmin Song, other collaborators from across the world, Timo Drabzuk, Yanta Rui, Caroline Burke, Hung, Elena, and Andres, who have been associated since we met in Cardiff in 2011, I believe, 2010. All right, so let me start my presentation by giving a research vision. You see 3 pictures here on this slide. The extreme left is, could be a melting or a solidification of an ice or water. The one that is at the center is, a crack propagation, either due to a static loading or a dynamic loading or a fatigue loading in structural members or engine metals. The last picture on the extreme right is a picture about showing how a flame propagates in a fuel or in a combustible medium. Although they come from different physics, they depict different physics. There is one common phenomena that is existing across these physics. The common phenomena is that there is an interface, and this interface evolves in time, right? So if you look at the first example, there is a solid-liquid interface which sort of evolves in time due to certain physics, governing physics. In the picture at the center, you have a crack phase. Due to some external loads, this crack phase starts to propagate. So there is an interface that moves in time. The same applies to the last case also, where there is a flame front, which evolves or changes its shape due to certain other conditions. So my research vision is to look at the centrality of a mathematical formulation across the discipline so that we can have an impact on a variety of fields. So predominantly my focus is not specific to one class of problems, say solid mechanics, but I look at general differential equation and see how I can solve them efficiently using computers. And in particular, I'm interested in looking at moving boundary or free boundary problems because they have wide applications in a variety of fields. For example, you can try to simulate baking of a cake to a tumor growth. It could also be used for assessing damage in complex structures. So my interest is to come up with common building blocks which can help us make progress in a range of disciplines. Okay? Although today my focus would be mostly on metals and how crack growth can be modeled using some of the new techniques, but a similar framework can be adopted to other physics, for example. So computational mechanics, as we know, has revolutionized the design, so it can probe into areas where theoretical or experimental investigations are difficult. So it is applied to civil, structural, biomedical. It's also used in finance modeling. You name it, computational mechanics has a role to play now. And a typical framework is what is shown here, is that let's say that you have a physical problem, and this physical problem is discrete in nature, and we try to understand what is going on with this physical problem. The way we do it is to get help from mathematics. So we seek help of a mathematical modeling and observe the physical formula and convert that into a set of differential equations. And hope that by looking at the solution of the differential equations, we can interpret or understand the physical problem. For example, if I'm looking at the stresses in the turbulent blade, I would pose this as a set of differential equation and then try to solve this differential equation to understand the response, for example, that is shown on the extreme right with a color counter plot. But the problem lies in solving this differential equation. So these differential equations are continuous form, and for complex structures, complex boundary conditions, there is no way you can get a closed form solution. And that's when we go back and look at, use numerical techniques to solve these differential equations. And the primary goal of these numerical techniques is to convert these differential equations, which are in a continuous form, into a set of algebraic equations. And then we use algebraic, concepts from linear algebra to solve for the numerical solution, right? Because we want to use computers to solve it, and computers works with numbers. So that's the reason why we do it. And there are a variety of methods which are currently in use, which help us solve these differential equations. And since all of them are approximation techniques, each have their own advantages and disadvantages. So I've listed some of them here, like finite elements, least square, finite volume method, spectral element method, boundary element method, collocation, finite difference, Ritz-Galerkin, and so on and so forth. And of these, for solid mechanics problem, finite element is the most sought out because of its strong mathematical background, its robustness, and there is almost 3 decades of research that has gone into finite elements, which is now widely accepted by industry also. We have sophisticated commercial softwares, robust commercial softwares like Abacus and ANSYS, the results of which can be trusted. But the whole idea is we should keep in mind is that the role of numerical simulation is not to replace experimental observations, but to help understand what we observe experimentally, or to reduce the number of experiments that we would have to do to come up with a design which is feasible. So if I want to pose this in a mathematical framework, the governing equations are given by differential equations. Like I said, a differential equation. So where LU equal to L equal to F, that's on the domain. L is some differential operator. And we invoke concept of Galerkin, and then we try to write the equivalent weak form for it. And then we try to find the solution, which is the approximate solution in terms of some polynomials. So this is the mathematical framework. And simple words, what we do is we try to divide the region into smaller regions, right? So for example, if I'm trying to look at some physics over a circle, I divide the circle into smaller regions. So the simplest region could be a triangle. It could also be quadrilaterals or polygons. But these have to be non-overlapping. For example, that is most used method. And by assuming the solution over each of these smaller regions, we can now construct the global solution. That's how it works. And the same idea also works in case of 3 dimensions, where the domain can be discretized or divided into non-overlapping elements. So the standard elements that are used in 3 dimensions are tetrahedrals or hexahedral elements, which are 6-sided or 6-faced elements. And the typical process in design is that you have a CAD model, and this CAD model is not suitable for analysis because this has complex shapes, and then it's not suitable for analysis. So what we do is we spend a lot of time converting the CAD model to analysis suitable model. This process, we call it as meshing, and many times meshing is the most expensive step in this whole process. And once you have the mesh, then you can adopt any of the previously said approaches to find the solution over this domain. And if it is not feasible, then you go back fixing the CAD model. And this is a typical cycle for design evolution. However, finite element is very robust. It's commercially acceptable. There are some setbacks with finite elements. I've listed some of them here, which are more critical than the rest. For example, the regions that we try to discretize have to have some nice qualities, properties of it. the foremost property is that the elements cannot be concave. For example, it doesn't allow elements to have concave regions because then the finite element breaks down. Or it cannot have very long elements which loses some good approximation properties. Although we may start with the good quality element, because of the theoretical framework, for example, if you're trying to solve a large deformation problem, we may end up with elements which are badly shaped. And then the analysis breaks down, so we have to stop the analysis, do something called a remeshing, and then start the analysis again. So that is a bottleneck if you're trying to use finite elements. And the other problem with finite element is that it requires conforming mesh to represent internal boundaries. And since we are using polynomials to represent the solution, if there is a sharp gradient or a singularity, finite elements sort of struggles to represent it. And we need extremely refined mesh close to the singularity. For example, you can see there is a red mesh here where the mesh is really fine, which is required to capture the singularity there. And also, you need to have a conforming mesh. For example, the black lines could be a representative grain. For example, if you're talking about polycrystalline materials, and you need to have a mesh that sort of conforms to these grains. And if these grains start to change shapes or evolve, I would have to update my finite element mesh, which sometimes could be not a trivial task to do. The last of the difficulty that I mentioned here is to do with geometry representation, because we use polynomials to represent it, and many times polynomials are not good at representation of actual engineering structures. For example, if you have really complicated shapes like this, you can see that the geometry is not exactly represented, and this introduces errors in your simulation. And as a stress analysis, we should be aware of these pitfalls of the finite element method. But this also has opened up a lot of research in trying to improve finite element method, right? And finite element method has also been used to understand material failure. So material failure could be an advantage or a disadvantage. So in this slide, I'm trying to showcase where it is not beneficial to have a material failure. And it's so important to understand when and how a material would fail. And if you're able to predict it, it's going to save a lot of monetary benefit. It will also save a lot of huge human life. And in this case, understanding damage mechanisms can help us design a structure which is damage tolerant. So we can avoid certain failures which are otherwise inevitable. Of course, understanding damage mechanisms also help us come up with a better tool design, so that we know what tool to use, to manufacture certain component, right? Because we should be able to remove materials or drill holes in certain materials for which we need to understand how the damage mechanisms appear in certain materials. So a conventional finite element method would require, like I said earlier, a conforming mesh. So here I'm showing two examples. The one on the extreme right, where you see a red line. This could represent, for example, a crack. And let's say this is subjected to some loading. It could be a tension or some fatigue loading. If we were to use finite elements, every time the crack moves, we would have to update the mesh, which could be not a trivial task, especially if you're talking about multiple cracks, especially in 3 dimensions. This is an example of typical example where it could be a phase change problems, like what we've seen in a solidification problem, where you have 2 different phases, and then this orange line depicts the interface of these 2 phases. And with change in time, the shape of the interface changes. And if you were to use finite elements, we would have to update the mesh every time it changes. And updation is not the only key. We would also have to port the information from the previous mesh to the new mesh for subsequent analysis, which may introduce certain errors in the simulation. And like I said, this has opened up a lot of research activities to come up with efficient techniques to model these moving boundary problems with finite elements. Yeah? And in, like I said, in this talk, I'll focus more on fraction mechanics. There have been a lot of work on improving or using finite elements to solve crack growth problems in materials. The first one is based on remeshing finite element, the one that we saw in the earlier slide, where the mesh is updated every time the crack grows in time or changes shape, right? Early 1990s, there was this method that was introduced called the extended finite element method, which is now also available in Abacus as an add-on, which the beauty of this method is that it doesn't need a conforming mesh to capture the crack growth. So the crack can independently grow on a background mesh, right? So that is the beauty of it. There is also this formulation called peridynamics, which works on integral formulation, which is also currently being heavily researched on to model fracture growth. And late 2000, there has been this idea of using phase field method, which is originally used for modeling phase change materials. Now people are trying to use phase field models to model crack growth in materials. Right? And in today's talk, I will focus on 3 topics: extended finite element method. I'll briefly touch upon a method called scale boundary finite element method, which has some nice advantages. And lastly, I'll touch upon phase field method to show. So the first of the topic is going to be on extended finite element method. So this comes under a bigger umbrella of methods called partition of unity method. And here the idea is to detach geometry and analysis. Remember, we talked about finite element method requires a conforming mesh. So now here the whole idea is that is it possible to come up with a method where the geometry can be independent of the mesh, and that's how the extend works. So the basic idea was. Excuse me, is there a question?
No, you can continue, Sundar.
So the objective of this is that if I have an interface, for example, a circular interface or some flower-shaped interface or a crack shown by a solid black line, is it possible to represent them independent of the mesh? Not only represent them, but I also capture the underlying physics, which is without a mesh that conforms to it, right? And conventional finite element would require that you need a conforming mesh. For example, if I'm trying to solve a crack problem, I need to have singular elements which are aligned to the interface. And you also need to have extremely refined mesh close to the crack tip so that you can capture the singularity. Remember, finite element works with simple polynomials, and polynomials are not really good in capturing the singular functions. Although if it is a static crack or a static interface, coming up with a mesh is not a problem, even in 3 dimensions. But the real problem comes when you have these interfaces that start to change shape or evolve in time. And this becomes computationally expensive if you are talking in terms of 3 dimensions, or if you have like multiple cracks, right, or multiple holes or inclusions. And conventional finite element method would have to differentiate a hole and an inclusion, whereas in XFEM, they can be treated in a unified way by just using appropriate AND-sorts or enrichment functions, which you will see in a couple of slides coming from now. And it's very robust in that sense. It can also model crack growth. It can also have these cracks coalesce, branch. It can do all sort of things with a mesh that doesn't update every time. All right, so when do we need enrichment technique? So we need enrichment techniques when you have discontinuities in your model, for example, cracks or material interfaces. If you have large gradients like yield lines or shock waves, or if you have singularities, for example, not just cracks, or if there is a re-entrant corner, or if there is a boundary layer in your problem, like it could be a fluid-solid or a fluid-fluid interactions, or if you're solution is highly oscillatory. For example, if you're trying to solve a Helmholtz equation and looking at mid-frequency or high-frequency problems where the solution is highly oscillatory, and we know that a typical number of elements that is required to capture is that you need at least 10 elements to capture the wavelength. So now if I'm looking at a really high frequency, my computational expense just grows exponentially. But by using XFEM, we can, we don't have to use such a highly refined mesh, but still capture the essential physics of the problem. And the basic idea is that we will add certain functions to finite element basis that can capture the necessary physics. Okay, and the basic idea behind that would be to improve the convergence rate, because when you use finite elements to solve these problems, the optimal rate of convergence reduces by 1/2 for certain cases. So we would want to retain optimal order of convergence with finite elements, at the same time capture the necessary physics with a mesh that doesn't conform to the geometry. That's a whole objective. So this is one example how people try to model cracks. For example, they use what is called a quarter point element, which is a special case of an 8-noded serendipity element, where they place the crack tip on one of the nodes, corner nodes, and they move the mid-side node to 1/4 of a distance from the crack tip. And by doing this, we can capture the singularity that is present at the crack tip. But this works for isotropic homogeneous material, but for other cases, it doesn't really work that efficiently. So that is also one reason why there has been a lot of research in coming up with methods that can capture the physics of the problem. For example, if it is a bimaterial interface and then you have a crack between those interfaces, the singularity is complex. So this sort of an arrangement does not work in favor of that. So again, like I said, there has been a lot of work in trying to improve finite element method, and I've classified them into 3 categories. They all come under a category called enrichment techniques. So one is called a local enrichment, global enrichment, and there is something called a mesh overlay techniques. The basic idea in all of these is to have a method where I can model these cracks or discontinuities independent of the mesh, right? And in this talk, I'm going to focus only on XFEM, although the same sort of a framework can be talked in terms of generalized finite element method or elemental enrichment techniques and other techniques. Okay, so the basic idea in XFEM is that you have the standard finite element basis function, and to it you add certain functions that carry the necessary information of the problem, right? So we don't know a priori what these functions are, but I know that if I can put in these functions, I can capture the physics of the problem. So for example, the first term, which is shown in blue color, that's a standard approximation for your unknown field. The one that is shown as PU enriched is the new function that we are going to add to the standard finite element basis. So here phi j's are standard finite element functions. Psi i's are the functions which carry the necessary local information of the problem. So if I'm trying to solve a wave problem, psi of x could be some sines and cosines, which represent the wavy nature. For a different set of problems, psi will take a different form. So now you can already see that by just changing psi of x, we can solve different class of problems, which a finite element method cannot do it, because finite element method is restricted to use only polynomials. But now here with this addition of psi of x, I have more freedom in choice of the functions. And the function choice will depend on the type of problem that we are trying to solve. So now that we are adding new functions, we also have to, since we are using Galerkin framework, we also have additional unknowns to solve for. And the rest of the process is going to be very similar to a standard Galerkin framework. We put that into the weak form, we compute your stiffness matrix and the force vector. But the only change now here is that because of this additional set of functions that we have added to the approximation function, the stiffness matrix now has an enlarged form, right? So it can be seen as a block form where the first block corresponds to the standard part, the last block corresponds to the enriched part, and then you have this coupling because there is an interplay between the standard and the enriched part. And by solving these, you can now find the coefficients, and then plugging it back, you can find the solution. And based on the choice of the enrichment function, the solution is going to be enriched, and that's the reason why these are called enrichment techniques. So this is how it works. So you see the standard finite element basis function that is shown for a 4-noded quadrilateral element on the left. You can see that at most it can only capture a hat type of a function, right? You can reproduce a hat type of function. So what we do in XFEM is that we take this hat function, multiply, let's say some function g of x, to get a new function, which now you can see that it is complex than your hat function. All right. So the choice of g of x is where we have a room to play, and depending on the type of the problem, we will choose a particular g of x. So we can use the same mesh. Depending on the choice of g of x, I can solve a crack problem or a problem with a void or an intrusion. It doesn't matter. So I can have the same mesh for all class of problems. Right. The way it works is that you would have to sort of represent these interfaces implicitly, right? Because now we are talking about a method where the interfaces are not represented explicitly. So we need to have a technique by which you can represent them. And typically we use level sets to represent the interface. And once we know what sort of problem that we are trying to solve, we need to identify the choice of an enrichment function. Like I said earlier, depending on the type of the problem, for example, if it is a wave problem, the functions could be, sines and cosines or some exponential basis. If it is a crack problem, we'll see what functions that we use. So this is the choice of enrichment function is completely upon us. So depending on the problem, we can change. And we also have to identify the regions where we want to enrich. For example, if it is a wave problem, we don't have a choice. We have to enrich the entire space because wave can go through the entire domain. But if it is a crack or an interface problem, we know that the deformation or the influence is going to be very local. So we don't want to be enriching the entire space, whereas instead we would want to enrich it locally. And to be able to do that, we need to identify the nodes where we have to enrich it. The other other thing that we have to worry about in XFEM is that since we are adding these new functions which are not necessarily polynomials, and they are represented implicitly, numerical integration of the weak form is not going to be a trivial task. And typically what is done is that we use triangulation to sort of find the integration points and compute the bilinear form. But it is noted that these triangles or subtriangulation do not add additional degrees of freedom. They are just there to locate the integration points such that the integration points do not lie on the interface, so that you are able to compute the weak form numerically. All right. So let's talk about how do we represent a crack independent of the mesh. So crack has, for example, if I'm talking about linear elastic fracture mechanics, crack has two distinct features. One is that there is a singularity at the crack tip. The functions, the stresses go to infinity as you approach the crack tip. And behind the crack tip, you have a jump in the displacement. So these are two different physics that I would like to capture. And if you're using finite elements, one that is represented by the black standard part, since the function ni of x, those are the basis function, they are continuous functions, they cannot represent either the crack tip singularity or the jump in the solution, right? And to be able to model this, we add two set of enrichment functions here. One that can capture the jump. So these functions are restricted to regions behind the crack tip, and one set of functions which can represent the singularity, so which is ahead of the crack tip. And by doing this, we can now capture the necessary physics of the problem without having to update the mesh. Now, if we have, let's say, a hole or an inclusion in the problem, we can add additional enrichment functions that will carry the necessary information. So to represent the jump behind the crack phase, all we have to do is add what is called a Heaviside function. So the derivative of this, the function itself is discontinuous and the derivative does not exist, so you can capture the jump. The functions that we use to represent singularity, comes from analytical expansions. For example, there are William expansions and other techniques which we can use them as enrichment functions. And sometimes if analytical solutions are not available, what we can do is to do one set, overkill finite element method, and then use that solution as an enrichment function for subsequent analysis. This greatly, saves computational effort. Everything is nice, but there are some difficulties with XFEM. Is like I said, integrating these complex functions are not going to be a trivial task, and it poses some challenges. However, by now, we know how to sort of work around these complex functions to do it. But nonetheless, these are some things that we have to keep in mind when we are trying to implement XFEM in this. The other difficulty is that when we are using local enrichment functions, there would be regions where the nodes are completely enriched. There will be regions where the nodes are not enriched, but there will be regions where they are partially enriched. And these are called blending elements in XFEM literature. And the problem with blending elements is that the solution is not represented accurately in those elements. And this leads to poor convergence rates and, some problems with the solution. Again, now it is all handled very nicely, so we don't have any blending problem. The other difficulty is that the conditioning number of XFEM, grows exponentially because of these additional enrichment functions. So care has to be taken such that the functions that we add to finite element basis are not linearly dependent on the standard finite element basis function. So if they are linearly dependent, we end up with a system which are linearly dependent, and then your conditioning number goes up, you will not be able to solve the system. And lastly, since we are adding additional functions, we have additional unknowns. Now, the price to pay here is that we would have to solve an enlarged system as opposed to just solving for the standard degrees of freedom. But again, there is a trade-off between that when compared to finite element method, which we'll see in some of the examples where conventional finite element method breaks down, whereas XFEM has a clear advantage in this. So the advantage of XFEM is the following. The one that you see on the top animation is what we saw earlier, which is conventional finite element method. What we see in the bottom figure is what we can achieve using extended finite element method. I can assure you that none of them are animated or they are coming from real simulation. So you can see that I don't have to update the mesh every time the crack grows in time or the topology changes or the interface changes in time. So that's an advantage with XFEM. Right, so we have applied this to many benchmark problems. One of the standard or classical problem is an experimental test case where you have a 3-point bend specimen with 3 holes, and there is a crack of length A, which is at the distance of D from the center line where the load is applied. And depending on the distance D, the crack would either go into the first hole, the bottommost hole, or it would bypass the first hole, go and merge into the second hole. And this is computationally very challenging to capture this because you need to have an extremely refined mesh if I'm using a finite element method to do it. And you also have to update the mesh every time the crack grows. And what you see on the right, the red line and the purple line are the crack growth from the experiments. And we try to solve this using XFEM. that's the animation that you would see. So this is a case where the distance is such that it sort of bypasses the first hole and then goes and merges into the second hole. So as you can see, there is a good correlation between experiments and the numerical simulation. And I would like to bring it to note, you notice that the finite background mesh was not updated during the entire simulation. So only the regions which have to be enriched was updated, but the mesh remained the same. So this is another example which was done by a student with Stephen Borders. This was for an industry where they were trying to look at how and when the fracture happens in a silicon wafer. So this was called a smart cut TM. So the basic idea is that you want to have a silicon wafer model where you want to sort of etch the wafer, and you would want to know when and what rate you can etch so that the wafer doesn't break. Right? So this is a complex phenomena, and our objective in XFM was to understand or model microcrack nucleations, and there would be multiple cracks which are happening, and these cracks may grow in time. They also can coalesce or branch out, and we would want to study these patterns and how this crack grows. We would also wanted to find the time to complete fracture and what is the final surface roughness, because every time the crack grows, it creates a new surface, and we would want to see what is the resultant surface. Because this crack growth is depending on the manufacturing process, so we would want to minimize the surface roughness. So if you are able to predict a priori what would be the surface roughness for a particular manufacturing process, we can go and then optimize the process by which you can then minimize the surface roughness. So this has multiple regions. We have a silicon, then a damage zone, and then some silicon wafer, and then silicon dioxide, right? And within the damage zone, you have multiple cracks, and this is the region where you would sort of etch so that you get the wafer out. And to model this, we have used cohesive elements and linear elastic fracture mechanics in combination with XFM, because you will see that there are hundreds of cracks when this is going to be etched, and then these cracks can grow in time. So here is an animation of the process. So I'm going to stop here. So what you see here is a small window of the entire specimen, where all these white lines represent the crack, right? And this is now subjected to some load, and there are some crack face loads that are also applied, which causes the cracks to grow. And normally we would expect that not all cracks grow at the same time. Some cracks grow and then stop because of the energy criteria, and then we are able to simulate that using XFM. So let the animation go. As you can see that the crack at the left mode started to grow. It started to merge with other cracks, and then it stopped for a moment. Then it started to grow in the other direction. And for the entire simulation, the mesh was not updated. We kept the mesh the same. Only the regions which have to be enriched have been updated. And you can already see that although there are other micro cracks, they do not actually participate in the crack path. So this is a nice thing. Although there are micro cracks, they don't necessarily become a macro crack, which may lead to essential failure. So we also have applied XFM to look at fracture in laminated composites. So laminated composites have typically two distinct fracture behavior. One is interlaminar delamination or fiber breakage, right? Or matrix cracking or fiber breakage. So this is a experimental video where you have a composite plate. It's a laminated plate, and you have two slots. The black solid black lines that you see on the image are the cracks, and then this is subjected to far field tension. So you'll see that the crack starts to propagate from this line, and it fails in an instant. And this is a typical quasi-static brittle failure. I can see that at about this frame, the crack, just started, and you can see that you're able to see there are some fibers that are also hanging out because of the fracture that happened. And our objective was to see if we can use XFEM to simulate this this observation. So those are the crack which are growing along the crack fiber. The fiber is along that direction, and since fiber is stiffer than a matrix, you can see that the crack has grown along a particular direction, along the fiber direction. So now this can help us design structures where we can optimize the layout of the fibers such that if at all there is a crack or a discontinuity, it can sort of delay the fracture process. So you can engineer the fiber orientation such that the crack takes a longer time to grow, which implies that we can increase the life of the component. Right. So, but to be able to use XFEM to do it, we had to come up with a new set of enrichment functions, because the isotropic enrichment functions that we were using for isotropic material were not able to capture the necessary physics, because it failed to have this information of the fibers in the model. So we had to come up with new functions. So these are the new functions where G of theta or G1 of theta, G2 of theta has the necessary information of the fiber orientation. And so we are able to see that we are able to model the crack growth in this orthotropic material using XFEM, and that closely matches with experimental results. So these are other configurations that we had modeled where the fiber is oriented along the one direction. And in this case, for a uniform tension, the crack is expected to grow, straight as expected. For the other direction, you can see that the crack goes along the direction of fiber. The one exception of this is when the crack is oriented perpendicular to the crack. Experiments show that there is the branch and that happens at the crack tip, which the XFEM was not able to capture it. That is because crack branching has to be an input to the model, so that it knows when the crack has to branch. So of course, when we did this simulation back in 2011, we didn't have that necessary information. So that's the reason why it was predicting that the crack grows along one direction and not in two directions, as we see in experiments. Okay, I think that's the last slide on XFEM. So are there any questions, or I can move on with the next part of the talk?
Sundar, okay, so we have two questions so far. The first one is related to what kind of software are you using to model these slides, the problems shown in these slides?
So we have developed our in-house codes. Some of them are in MATLAB, some of them are in C++. They are also available in our GitHub source page. I can share the link with Andres, who can share it with you guys. We also have implemented this in Abacus, but by the time we've implemented, Abacus also has its own module on XFEM. But all these simulations are based on in-house codes.
Okay. And also, one attendee is asking your opinion regarding the virtual element method for fracture mechanics.
Can you repeat that question?
Somebody wants to know your opinion regarding the virtual element method, VEM.
Yes, in fact, we have started to look at enriched virtual element method. So I see virtual element method as a way to compute the bilinear forms leaving aside these discontinuities or anything in an efficient way without having to worry about the shape and the size of the element. It still uses polynomials to represent the unknown fields, which is still a problem if you're trying to use to model crack problems or in interface problems. Of course, the research is in a very slow process. There is one paper by Sukumar and others where they have tried to model a crack in a scalar problem, but I think there is still a long way to go doing it. But I think the research has really picked up using phase field method, which is really a hot topic now.
Okay, the same person, I think it's Jorge, is asking if you know information about the matrix material in the carbon composite that you showed in the simulations. It's a standard prepec, I suppose. Hi, Sundar, we don't have your audio. We lost your audio, Sundar. Can you hear us? Sundar?
Yeah, I think we lost the audio.
I'm going to write to him.
Hello?
Yes, Sundar, I can hear you now.
Yeah, it kicked me out. I don't know why.
Okay.
So
somebody, okay, so a couple of more questions. Somebody's asking if you know the matrix material for the composite, for the carbon composite that you are showing there.
The matrix material is epoxy that we have used.
Okay, so it's a standard prepec. And the last question to continue, how can XFEM be used for plate fixation methods in framework bond fracture? Which dynamic failure model to be used for titanium alloys regarding the fixation, regarding the crack?
Okay, so XFEM is a numerical technique which allows us to model these cracks independent of the background mesh. How the crack grows, when grows, in what direction, when it has to coalesce, when it has to branch, what sort of a damage criteria that we have to use, or these are all inputs to the method. It has nothing to do with XFEM itself, right? So that is a different area by itself, where what sort of criteria that I have to use to model the crack growth. In these cases, what we have used is a maximum stress criteria, which sort of was okay for these materials and these experimental simulations. But for a general case, yeah, those have to be known a priori as to what to use.
Okay. Thank you, Sundar. I think we can continue to the next part of the conference.
Oh, thank you. So the next part of my talk is going to be on scale boundary finite element method. So I'm going to be very brief on this method because there is a lot of math involved, but I'd just like to touch upon the benefits of the method without going into much of the details of it. Right? So here the idea is you can reduce the dimensionality of the problem, right? So you can see that it has boundary, it also has finite element method, and if you have guessed it, yeah, it's right. So it has a combination of the techniques that we use in boundary element method, and it has the advantages or the techniques that we use in finite element method. And scaled, we'll try to understand as we move along with the method. So a brief on what this method is. So this was originally developed for soil structure interaction problems. The first paper appeared in 1997. It's a semi-analytical procedure. And since then, it has been applied to several other fields such as fraction mechanics, fluid structure interaction, acoustics, electromagnetisms, and very recently polytopes, and this was extended during my postdoc at UNSW. The beauty of is that only the boundary is discretized, which implies that the volume need not be discretized. So that is a major plus point. And since it's only boundary is discretized, it looks like a boundary element method, but it doesn't require, the beauty of this, it doesn't require any fundamental solutions like the boundary element method. So it implies that I can directly apply this to a material nonlinearity problem or a geometric nonlinearity problem without any difficulty. And it also works really nice if you're looking at infinite domain problems where the boundary conditions and the infinity can be exactly satisfied, right? Because it's semi-analytical in nature. So here is a conceptual comparison between a finite element and boundary element method. So here I've taken the same example. I would like to model an edge crack problem with finite element method. You can see that the mesh has to conform to the crack, which is at the middle. Of course, the mesh is not fine enough, but this is a schematic representation of what a finite element method would require. Boundary element method, on the other hand, would discretize only the boundary of the domain, and it uses Green's function, a fundamental solution, to represent the solution inside the domain. So the benefit, or the boundary element method requires this Green's function, which sort of is a disadvantage when trying to apply to a general class of problems. Whereas a scale boundary is a combination of both. So like boundary element method, it discretizes only the boundary, and like finite element method, it does not require a fundamental solution. So that's how it works. So here are some of advantages. It reduces spatial dimension by 1 like boundary element method. It uses analytical solution inside the domain. It does not require fundamental solution like finite element method. It does not require the material interfaces to be discretized, which cannot be done in either finite element or boundary element method. The beauty of it is that the resulting stiffness matrix is symmetric and positive definite like finite element method. Whereas in a boundary element method, if you're not using special techniques, it becomes unsymmetric matrix. And if you're trying to look at fraction mechanics problems, we can compute the stress intensity factor in a straightforward manner without having to go through the J integral route or a virtual crack closure technique approach. And it can be seamlessly integrated with finite element method. That's the beauty of it. If you have an existing finite element code, you can directly, with a very minimum modification, we can make the code to be a scale boundary code, and then you can solve some nice problems with it. All right. So the basic idea with scale boundary is that you work with a different set of coordinates. All right. So you start by defining a new set of coordinates called the scale boundary coordinates. And this coordinate is situated inside the domain. And the criteria is that from the coordinate, you are able to see the entire domain. Okay. So, and on the boundary, we use finite elements to discretize or represent the boundary. Right? And now I can go from this coordinate to the boundary by just scaling. So for example, if I represent the coordinate from the origin O to the boundary as psi, which goes from 0 to 1, by changing the value of psi, I can go from the coordinate 0 to the boundary, and that's why it's called a scale boundary coordinate, scale boundary finite element method. It's finite element method because on the boundary it is finite element method. Of course, we also have applied, for example, isogeometric analysis, because the CAD software gives only boundary information. And if we were to use an isogeometric analysis framework, we need to have volume information. That becomes quite a challenging task. But if we use scale boundary finite element method or scale boundary technique, we can directly use the CAD model for analysis, because CAD gives boundary information and scale boundary requires only boundary information for solution. So this is sort of nice thing that we can work on. So the rest of the formulation is going to be very straightforward. We transform the displacements. We also transform the strain to these new coordinates. We plug that back, all of them into the virtual work, and that gives us to a stiffness matrix which looks exactly similar to a finite element matrix. But here the beauty is that these integrals are going to be only on the boundary of the domain, nothing.
Sundar, we lost Tavi again.
If I have a domain with a crack, all we have to do is to place this coordinate origin at the crack tip and then sort of scale to the entire boundary. And since we are representing the solution inside the domain using analytical expressions, analytical functions, these analytical functions carry the necessary information of the problem. So we don't need to know a priori what is the strength of the singularity, whereas the singularity comes as an outcome of the solution. So that's the beauty of the method. And it helps us capture, or rather compute the stress intensity factor, not only stress intensity factor, but also T stress and M stress and so on and so forth, which could be essential for certain materials. So this is one classical example where you have a plate with an inclined crack of length 2a, and it's subjected to far field tension. If you look at a finite element mesh, you will see that the mesh has to be extremely fine, close to the crack tip. Whereas in scale boundary, the one that you see at the middle is all what you require to solve the problem. So first of all, you can immediately see that the number of degrees of freedom is going to be extremely small. So the solution is going to be super fast. You can also use your laptop and just run the model. It's that efficient. In terms of accuracy, you can see that the stress intensity factor K1 and K2 are very close to what is reported in the literature, right? And this has also been compared with boundary element method. It gives very similar results to boundary element method. But here I would like to emphasize that it doesn't require a Green's functions to do it. But the catch here is that if this crack starts to evolve, this sort of a scaling requirement where I said from the origin I should be able to see the boundary sort of vanishes. So to be able to do it, we again sort of discretize the domain into smaller regions, and over these smaller regions we can use scale boundary to do it. So here is one example where we don't have to have a structured grid. We can discretize the domain with polygonal elements, and you can sort of capture the crack growth using scale boundary with a minimal effort as compared to a finite element method. Of course, here I'm not comparing with the XFEM, but this is a comparison with the conventional finite element method. So that's sort of a quick overview of scale boundary method. I should also here point out that it's still not applicable for three-dimensional crack growth problems. There is still a long way to go if you're able to model that crack in 3 dimensions, because this scaling requirement, it's tricky in 3 dimensions because it doesn't boil down to a point. It boils down to a line, which sort of, we're still trying to come up with the transformation which can, transform the coordinates such that you're able to use scale boundary technique to do it. So, but if you're talking about 2-dimensional problems, I think scale boundary, is most efficient than any of the techniques that are available, and it's more accurate for a given degrees of freedom. And you can actually run it on a desktop with, let's say, a 2 or 4 GB RAM, and you will get accuracy, very high accurate results. Yeah. Are there any questions before I move on to the last part of the talk?
Yes, Sundar. Okay, this is related to XFAN again.
Yep.
Baby Garcia is asking if this XFAN approach could be extrapolated to materials degraded by temperature, like cases when creep is expected.
Yes, it can also be applied to to those problems, thermodynamic problems or chemomechanic problems. In fact, when I was doing my PhD, there was another PhD student called Alexander Menk. So his PhD was on looking at thermomechanical fatigue on solder joints that are used in boards in the car. So where he has used XFAM to look at how the cracks propagate and what leads to final failure. Yeah. So in short, yes, we can apply to multi-physics problems.
Okay, and also Sergio Munoz is asking if it is possible to model solidifying cracking seeing the casting and welding processes.
I'm sorry, can you repeat the question?
If it is possible to model solidifying cracking as the cracks that appear when you are modeling casting and welding manufacturing processes.
It is okay. In principle, yes, but as we know, the cracks that form during solidification or welding are really complex, and there are cases where the cracks sort of coalesce or branch. So if you are able to have that information about when to branch or when to coalesce, yes, XFAM can be used to do that also. But
okay,
for those problems, currently I would suggest that phase fill method would be an ideal way to go about doing it, because we just submitted a paper where we had looked at a coupled thermomechanical problem where we look at how the cracks sort of evolve when a particular component is quenched. It's heated up to a particular temperature, and all of a sudden it is quenched in in a water bath, and then you'll see that there are microcracks that are evolving because of temperature gradient. And we tried to use XFAM, but then there were difficulties. Then we switched to phase fill method, and that works really nice at this stage.
Okay, thank you, Sundar. We can then move to the last part.
Thank you. All right. Okay, the last part of the talk is going to be on phase fill modeling, and here this is a variation approach to fracture as opposed to the other techniques that we have seen earlier. All right, so the basic idea here is that so this can be classified under a smeared or a diffuse crack model. So there are two ways by which you can represent a crack. One is a sharp crack, which can be represented discretely, either explicitly using conventional finite element method or implicitly using XFAM technique. In both the cases, you know that we need a criteria by which the crack grows, and then we need to update the mesh. In XFAM, we need to have this knowledge of enrichment functions, which for complex cases may not be available. Some cases, yes. But like I said, you also need to have a condition for a crack to branch and coalesce. If I have hundreds and thousands of cracks, XFAM, in my experience, has some difficulties. Okay. The other approach to model the cracks are diffuse models, and phase fill can be thought of as a smeared crack or diffuse crack model. And here the basic idea is that the total energy can be split into two energies. One is the bulk and the surface, because every time the crack is evolved or it's formed, there is a new surface that is formed. And for the crack to grow, there has to be an energy that is spent to form this new surface. So this is the basic idea of Griffith, and that's how the fracture mechanics came forward. And this bulk energy is a volume integral, whereas the surface energy is a line integral or a surface integral. And what we do is we use Gauss-Lagrange theorem to convert that surface integral to volume integral. Then you can then work with a variation framework to use phase field model. So the basic idea in phase field is that the crack can be represented or thought of as two different phases. Rather, the region where there is no crack, we call that to be an undamaged state. And there is a region where there is a crack, which is a damaged state. And the transition between the damaged state and undamaged state is what we call as a phase field variable. And typically it takes a value of 0 to 1. So 0 implies it's undamaged, 1 it is completely damaged. Now the question is, how do I go from 0 to 1? Right? So there are different ways by which you can do it. And typically, we use an exponential to sort of represent it. And to be able to model the width of the crack, we have this parameter called L0 that sort of dictates how sharp or wide the crack is. The larger the value, the thicker the crack, and the smaller the value, the sharper the crack is. Right? So, and this help us model, different complex cracks. It can have multiple cracks, and they can have intersecting cracks, and so on and so forth. And the beauty of it is that it can be readily extended to 3 dimensions, and you can use your existing finite element code to model phase field modeling cracks. The model cracks using phase field methods. If you have looked at the earlier methods like XFEM or scale boundary method, there is some amount of work that has to be done so that your code can adapt to it. But with phase field method, the beauty is that existing finite element code, it could be a finite element code or a mesh-free in isogeometric analysis, it can be directly used to solve the crack problems using phase field method. So what we do is that we convert the surface integral into the domain integral, and then we have this diffusion equation which sort of governs the crack evolution. And we have this bulk energy which we multiply with a degrading function, because we need to separate out the region which are completely damaged to the region which are undamaged. So we multiply with a function called a degradation function, here represented using g of phi. And this has to satisfy certain conditions. So it has to be g of 0 should be 1 when it is no damaged, and it should be 1 when it is fully damaged. And there are other conditions with respect to the gradient, which are necessary from a mathematical point of view. So there are different degradation functions that are used in the literature, and this sort of dictates how fast you go from a damaged to an undamaged state. There are quadratic variations, there are complex forms to it. The simplest one to implement would be the quadratic form, which is shown as a black line. So it takes a value of 1 at the crack tip, and it eventually goes to 0 away from the crack. Yeah. But this quadratic function would lead to a sharp discontinuity at the crack tip. There are some pros and cons to it, and there is still a lot of debate going on as to what would be a suitable functions to use it. That is still an open question to be answered. So now the total potential energy can be written as given by equation 6, where we have the first term is the bulk energy, second term is the energy coming from the phase field. We follow the same procedure. We take the variation with respect to the strain and also the phase field variable. So now you have to keep in mind, now we have to solve for the strain and also for this new variable called the phase field variable, which will dictate how the crack is going to evolve. And we follow the same variation framework. We end up with governing equations. The first equation is very similar if you ignore the factor, which is just the elasticity equation. So this equation is supplemented with a diffusion type equation, which is given by the second equation. GC is the fracture toughness, L0 is the phase field internal length, which sort of helps us model the crack. Remember, the smaller the value, the sharper the crack is. And this is supplemented with boundary conditions as before. And so this is a coupled problem because the stress equation has a phase field variable, and the phase field equation has this potential energy psi of epsilon. So to compute psi of epsilon, we need the stress information. So this is a coupled problem, and one way to decouple is to introduce a new variable called a history variable, which sort of depends on the strain information that is present or that is for a particular material point. Okay, so here is how it works. So we have to just use conventional finite element method to solve these two equations. We can write the weak form for it, and then we can use traditional elements to do it. And the point to note here is that the crack is not represented explicitly, but implicitly using the phase field variable. So I'm going to show you two examples. A classical example where you have a square block with a crack of length 0.5, and this is a tension. And there is another example where the same square block with a crack subjected to shear. So in the first case, you will expect that the crack grows in a straight form until it reaches the external boundary. In the shear case, because of the boundary conditions and the load applied, you will see that the crack sort of deviates, takes an angle and goes to one of the boundary, fixed boundary. So, so this is in a plot coming from the phase field equation. By solving it, what you see here is the crack trajectory. So the red indicates that that's a crack, and what I'm showing is here is a phase field variable. So blue represents 0, so which implies the rest of the domain is not damaged at all. And we sort of implemented that in our in-house code, and we compared the results of the load displacement curve with that's published in the literature. We are able to get some good match. So in case of a shear, if we use directly the phase field formulation that was put forth in the earlier work, you see that the crack branches, and this is unphysical if you are talking about quasi-static crack growth. And this was because the earlier model allowed the crack to grow also in the region where there is a compressive state of stress, which is not physical. So, and there has been a lot of work to avoid it. There has been approaches like additive decomposition of the strain into deviatoric and volumetric part. There has been decomposition based on eigenstrain, which sort of suppresses the crack to grow in the compressive region. And so that's a formulation behind it, where you sort of update the history variable only with the positive side of it, or only the tensile part of the energy. Whereas the negative side, if it is, you just ignore it so that the crack doesn't grow in the negative side. So if you're implementing it, you can then see that the crack sort of grows only in one direction, which is what is physical. Again, we implement this in our in-house code and compare this with the results in the literature. We are able to get a good match. Of course, sorry, this was implemented in Phoenix. Phoenix is an open source finite element software. We implement this in Phoenix, and then we are able to say get some good. All right. So all is nice with finite element method. It is elegant in modeling crack nucleation. It can also do crack propagation, branching. It can also model multiple cracks. They can coalesce or branch out. All is fine, but the problem is that it requires a highly refined mesh to resolve the necessary physics. Because of the variable L0, it requires a highly refined mesh. So what we sought out was to use local refinement techniques, and in particular, we wanted to use a scale bound refinement method, which has some nice features in terms of error indicators. And so that's how we started off this work. And we used the error indicator coming from a scale bound refinement method to propose an adaptive phase field model, phase field method. Here I'm going to skip this part of it. So this is the basic idea of what the scale boundary method is going to do. So we introduce a new coordinate system, which is called scale boundary coordinate system, from which the entire domain is visible. And all these equations are now converted to the scale boundary equations. So we end up with a similar set of equations like finite element method, like we saw in the previous part of the talk. So I'm not going to go into the details of it, of the mathematics. I'd like to just highlight on the nice advantages that this method can give us. All right, so scale boundary method, like we saw in the earlier part of the talk, is that the solution inside the domain is represented analytically. Okay, so this gives us nice advantages because now I can use this information to, or use this information as an error indicator. Because what this analytical solution does is that it gives integers powers and some non-integer powers. So integer power represents that the solution is represented exactly, whereas a non-integer power means that the solution is not represented exactly. And so it picks up those regions where the solution is not represented exactly and sort of refines this. So that's the basic idea of the error indicator in combination with this. And the way we do refinement is to start with a structured quadrilateral mesh, and we use quadtree decomposition because it is the most efficient way to divide the elements into, or rather refine the elements locally. So I'm going to skip this part. It's just telling you how to identify the regions using scale boundary indicator. So here's a flow chart of it. So we start with a mesh. We solve for the displacement. We solve for the phase field equation. Then we go and check if the mesh has to be defined. If it has to be refined, we go and update the mesh, solve the problem again so that we attain some equilibrium. If it need not be refined, then we go to the next load step, and then this process continues until we want to simulate it. Right. So here is the output of the simulation. This is the same problem, the shear problem. You can see that we start with a very coarse mesh, and with the error indicator, you can see that the mesh is refined close to the region where the crack is evolving, and you're able to still capture the necessary physics, the crack growth, as what we have seen in the previous slide. And you can see that the rest of the domain where the damage is not expected, the mesh is really coarse. And this is the typical quadtree sort of refinement, which helps us refine very locally, and it's very efficient also. And this also works in 3 dimensions, where instead of a quadtree, it becomes an octree type of refinement. Again, we have just submitted a paper on adaptive refinement in 3 dimensions. So here is an animation of how it works. I hope it works. So we start off with a very coarse mesh. Again, the red indicates that the material is damaged. The blue indicates the material is undamaged. This is now subjected to shear, and you can see that until a certain point of load, it doesn't move. And at a particular load, you can see that the elements are getting refined locally. And as it propagates, the mesh is refined. Right. I'll run it again so you can appreciate how it works. So by doing this, we have saved a lot of computational effort because we don't have to refine everywhere, which is what is required by conventional phase field method. So here is another example where I have multiple cracks. Again, we start off with a very coarse mesh, and we use the error indicator from scale boundary to identify the regions where we have to refine it. And you can see that the refinement happens locally. Of course, there is still some room for improvement where we can sort of get rid of the mesh behind the crack tip. We're still working on it. But in principle, it works. I'm going to run it again for you to visualize how the crack grows. And this is a typical example where, because of the strength of the singularities, you see that the crack sort of tries to go into each other. And the crack bends because of the singularity present because of the other crack. So we also have tried it with other complex scenarios where you have a void, you have some matrix, you have some fiber. This is some manufactured problem. The left end of the problem domain is restrained, whereas the right end you are subjecting it to a uniform tension, right? And here there are no cracks to start with, but because there are singularities or concentrations, we expect that the crack would start at some location depending on the state of stress, and the phase field method can sort of capture that. So the initial mesh, we started off with 6,000 and odd quarterly elements, and we'll see how it works. So the crack started at the top, the inclusion, and then it propagated all the way to the end.
Okay, we are losing audio again. Wait a minute.
Very small when compared to the standard phase field method. Of course, one may immediately see that the width of the crack is smaller in standard phase field method, whereas it is thicker in our proposed method. This can be controlled by increasing the number of elements close to the crack tip. Even then, you can already see that there is at least 2 orders of magnitude difference, so we will still be computationally efficient in doing it. I think that brings to the last slide of my talk. So in this talk, what I have done is presented the basic idea of XFEM, scale boundary finite method, and phase field modeling. We discussed with some standard benchmark problems in elasticity and linear elastic fracture mechanics. And I'd like to conclude my talk by thanking once again Andres and others for giving me an opportunity to talk in this network. I'll be happy to take any questions. And if you have any other questions or willing to, I'm open for collaborations if there is something that we can work on together. Send me an email. I've been asking Andres that we should start working together again. Once again, thank you for your time.
Okay, thank you, Sundar. Thanks a lot for your presentation on the recent advances on fracture mechanics using computational mechanics. We have a couple of questions more. Fidel Romero is asking, how can we introduce residual stresses, a profile of residual stresses on the models using XFEM or any other technique that you just show us?
So if I get the question right, so you're asking how do you model residual stresses in XFEM framework or phase field?
Yes, residual stresses.
So the residual stresses, in the way we model would be same as what we will typically do in finite method. Remember, again, these techniques are not going to eliminate finite method, but they are going to only give you additional flexibility to finite method. So whatever approach that we have been using to solve certain class of problems can still be the same procedure can be used in these approaches also. Does that answer?
I think it's okay. Also, Sergio Munoz is asking if it is possible to model solid state transformations and its mechanical properties changes as for example, the martensitic transformation due to strain in front of the crack tip in an austenitic steel?
I think I have seen a paper which talks about how to use phase fill model to model it. I personally haven't worked on those. I mean, if you're interested, I can forward the paper to Anders and then he can communicate that to you.
Okay, thank you.
Yeah. Because it has been used to simulate martensitic transformation, and that has been combined with the crack propagation also very recently. It's a very recent paper. I can share that with Anders later on.
Okay, thank you. Also, David Garcia is asking, what are the main limitations of XFEM, scale boundary FEM, etc., modeling industrial problems related especially to complex geometry, simultaneous loading conditions, response spectrum, random vibration, and so on. Mainly limitations of the current approaches.
Okay, so all these three approaches that we discussed today are approximation techniques. So they have their own advantages and disadvantages. For example, if I talk about phase fill method, like I said, we don't have to sort of modify the existing finite element code. I can still use the same finite element code, but I would have to solve two equations simultaneously to be able to model the crack growth problem. But the downside of that is that it's going to require you an extremely refined mesh to be able to capture the necessary crack path. Right? Of course, there are some research going on as to how to improve that, but that's I wouldn't at this time. Yes, you can call that as a disadvantage, but yeah, that can be worked upon. For scale boundary, like I said, a 3D crack growth problem is still a long way to go. But if it's going to be 2 dimensions, I think it is better than phase field and XFEM because the results are accurate. You can model them, very efficiently. We have some papers on dynamic crack growth using scale boundary where we have shown that it's computationally efficient and accurate than XFEM or finite element methods. The beauty of scale boundary in 2 dimensions is that you can also handle interface cracks, which are very difficult because enrichment functions, if you are using finite element method, require complex enrichment functions, and those are very difficult to implement and also integrate. XFEM, yeah, I mean, it has come a long way. I would say it's been 2 decades now. It has come a long way. It's more robust now, but there are still some difficulties with it because the first thing is you would have to change certain structure of your code to be able to implement XFEM to it. Criteria for crack growth, covalence, and branching are to be an input to the model, unlike a phase fill technique, because it is an outcome of the process. And the difficulty with XFEM is that you need to know a priori the enrichment functions. And the other difficulty, what we sort of foresaw in the multiple cracks is that when you have 2 cracks very close to each other, the strength of the singularity is not root R anymore in as what we see in isotropic material. And this overlapping of singular fields caused some convergence issues. So we had to use some locally refined mesh so that the singular fields do not overlap each other. Yeah, there are some difficulties with XFEM in those aspects also.
Okay.
Yeah.
Okay, thank you, Sundar. The last question, David Garcia also asks us if these approaches are currently incorporated in any commercial or industrial package. And, well, first that one.
Okay, like I said, XFEM is available in Abacus as a module. I think it's from version 6.8 or 9. It's available in Abacus. Scenario, a company, they have their own XFEM code, which I believe Andres knows about it. and many people have their own version of XFEM codes available. So to the best of my knowledge, at the moment, Abacus is the only commercial package that handle XFEM. But it also has certain limitations because it has implemented the part which is more tested. You know, there are some improvements on XFEM which has not been implemented in Abacus. Scale boundary, we have, our group has implemented a scale boundary in Abacus using user element routines. To the best of my knowledge, there are no commercially available softwares that can do it. Phase field again, it's only a fundamental code that you require, so you can use Abacus to do it. You can, the phase field equation can be thought of as a heat equation, so it's a scalar equation, so you can use user elements to use Abacus to solve it. Other than that, I'm not aware of any commercial software which can, solve, the phase field equation. We can get COMSOL to do it because COMSOL also works with coupled problems. Yeah, but other than that, I'm not aware of anything that has a ready-made module which can do phase field.
Okay, thank you, Sundar. I would like to thank all the people, all the attendees for their questions and also for being here with us. Sundar, thank you again for accepting our invitation. For the people attending the conference, certificates are available if you email to the organizers. The email is in the chat, is recov. Let me check. You have it in the chat and also in the flyer for this presentation. I don't remember where I saw it. Okay, it's investigación recov at gmail.com. There you can send an email with your name and details, and we will provide a certificate for the conference. Okay. We are right on schedule. Sundar, I think with this, we will finish the presentation. I don't know if anybody else wants to give any feedback or any last question before we finish. No questions so far. So thank you again. We hope we can collaborate. You have a Sundar email also, he showed it in the presentation. You can contact him or contact me to provide further information, propose any collaboration that you want with the IIT in Madras. And we hope that we can, of course, provide more webinars like this. We already talked with some colleagues from Sundar in Madras, and we expect them to accompany us in the future. So thank you again, everybody. Thank you, Sundar.
Thank you.
Have a nice day.
Thank you, Andres, and have a nice day. Hope.
Okay. Bye.